Okay, guys, let's get started. Last time we finished how to display our data by graphs. We have, of course, two types of data. We have categorical data and quantitative data. For the categorical data, we can display this type of data by uh, bar chart, pie chart, right? Remember that, okay? And for the quantitative data, we can display this type of data by the histogram, dot plots, right? If you remember, stem and leaf, okay? These three plots. And also, if we collect the data over the time, we can chart we can draw this data by time chart, or sometimes we call it line chart, okay? So these are um, graphs that we can use to display our data based on the type of each one of them. Today, we will start to calculate some statistics. And these statistics should be summarized, our data in a few groups of numbers, okay? So as you can see here, we will start with something called the measuring the center of quantitative data, or sometimes we call it the measures of central tendency. So what that means? That means we need to calculate where is the center of our data. Where is the center of our data, okay? So let's get started with the first one, or the first measure we have here. Actually, we have three measures. The first one is the mean. Sometimes we call it the average or the arithmetic average. We have another measures, we call it the median of the data. And the last one is the mode of the data, okay? So we start, as I said to you, with the mean or the average of the data. And as you can see here, to find the average or the mean of any quantitative data, all you need is to find the sum of the data we have or the measurements we have, and to divide it by the number of these measurements. So you will have the average or the mean of our data. As you can see here, we will distinguish between two measures here, the sample and the population, okay? If you calculate the measures from the sample, we call it statistics. When we calculate these measures from the population, we call it parameters, okay? So as you can see here, for the mean, if you would like to find the sample mean, and we give this measures, this symbol, X bar, as you can see here. So this is the symbol for the sample mean, X bar, we call it X bar, X bar. It's equal to the sum of xi, we call this the sum of xi divided by n. What is n? N represents here the number of measurements we have, or the number of data we have, okay? So for example, if you have 10 numbers, so the sample mean in this case will be the sum of these 10 numbers divided by 10, okay? This gives us the sample mean. With the same way, we can find the population mean. So if you measure all objects in our population, and you will calculate the mean from this population, in this case, we calculate the population mean. In this case, we have a parameter. So mu here, this symbol represent the population mean, and it's a parameter. It's not a statistics in this case, it's a parameter, okay? And again, we call it mu, okay? And as you can see, it's the same equation like x bar. It's the sum of x, which means we will find the sum of all measurements divided by the number of data in the entire population, as you can see here. So the difference between m with lowercase with the sample mean and the n, the uppercase with the population mean, that the lowercase n is the number of data in our sample. But in here, for the uppercase one, is the number of data in the entire population. This is the only difference thing. But what that means, it's the number of data we have. Okay, that's it. So this is the way of finding the mean or computing the mean of the data. So in this example, we need to find the mean of the serial sodium data, which means we need to find the center of this data. So as you can see here, we have 20 numbers or observations. Okay, we have 0, 340, 70, 140. Okay, and to find the mean, all you need to find the sum of all these data and divide it by the number of these data. We have here 20 numbers. So as you can see, the total numbers here, or the sum of all this number, is 3,340 divided by 20, the number of data we have. So the average here, or the mean of this data, is 167. So this is the center of our data. Because we use Excel, we will know some functions. The first one about the average or the mean. As you can see here in Excel, to find the mean, you will use average function. Average function, okay? So you will start with equal sign, the average or average function, and then you will select the data you would like to find the average for them, okay? If you have a calculator like TI, version of TI 830 or above of 83, so you can use this step. You will have there a start button, okay? Use it and select the first, we can say the first tab or the first choice there. It's number one about edit. You input the data there. It will be, it's like a table. So you will enter the data in the first column. This column is L1. And then you press stat again and choose the other menu, which is calc. This is the shortcut for calculation, okay? And select the one variable stats. One var, it's a variable, stats, statistics, okay? Choose them, you will have a list of most of the measurements we will see in this chapter, like the mean, the median, the mode, the standard deviation, the variance, the number of measurements. You will find this list. Okay, and also in Excel, you will know today how to find all these measurements in just 1 or 2 clicks. The second one is the median. The median. This is our second measure for the central tendency or for the center. So what is the median? As you can see from the definition here, is the middle value of our observation. The middle value of our observation, okay? But when, after you order the data from the smallest number to the largest number. So this is our first task. When you have the data and you would like to find the median, first order the data, put them in order from the smallest number to the largest number, or from the largest number to the smallest number, doesn't matter, okay? And then find the number in the middle of this data. This is the median, okay? And as you can see here, the median here, the calculation of the median is based on what? The location of the number, not the number itself. It's not like the mean. In the mean, you find the sum of the data and divide by the number of this data. So here, for the sum of the data, that means you use the number itself. But for the median, you put the data on order and define what the median, which is the number in the middle, which is the location. We are interested in the location of the number, not the number itself, okay? So this is the way to find the median. Of course, here we have 2 cases. The first case, if you have the number of data is odd, like 9, 7, 11, okay? We have odd number. This is the number of data. So in this case, you will have just one number in the middle, right? But if you have even number of data, or the number of data is even, okay? So in this case, you will have two numbers in the middle, right? Two numbers. In this case, the median will be between these two numbers, between these two numbers in the middle. And you can find that, just find the average of these two numbers or the mean of these two numbers, so you have the median, okay? So we have this example. As you can see here, find the median of the following sample. We have 5, 7, 4, 8, 7, 6, 2. First, you have to put them in order, okay? So we have 2, 4, 5, 6, 7, 7, and 8. How many numbers do we have here? 1, 2, 3, 4, 5, 6, 7. And the 7 is an odd number. So what that means? That means we have just one number in the middle. What is this number? It's what? It's 6, right? This is the only number in the middle, just one number. So the median is equal to 6 in this case. And as you can see here, before 6, you have 3 numbers, right? After 6, you have 3 numbers. So what that means? That means the median divide our data into 2 groups. 50% of the data before it, for the median, and 50% after the median. So because of that, we call it the median. Okay, because it's divide the data into 2 halves, or to 50% of the data before it, 50% of the data after it. What about the second case? Look at this example. Here you have 5, 7, 4, 8, 7, 6. How many numbers do we have here? We have 1, 2, 3, 4, 5, 6. 6 numbers. So it's an even number. What that means? That means you have here 2 numbers in the middle. So in the middle, we have here 6 and 7, right? The median is between these 2 numbers. So it's what? It's 6.5. How you can find it? Simply find the mean of these 2 numbers. 6 plus 7 divided by 2. So you have 6.5. That's it. So this is the median. So you have here in the middle, you have 6.5. Before it, you have 3 numbers. After it, you have 3 numbers. So 50% and 50% of the data before and after these two, this number, as you can see. How we can find the median? By Excel, like the average or the mean, you have a function here. You will start with equal sign, median, this is our function, and then select your data. So you will have the median in this case. This point is very important, the outlier. If you remember, I talked about the outlier a little bit in the previous meetings, because it's a very, very important one, because outliers here has a great effect on a lot of statistics we are dealing with, okay? So as you can see in this histogram, if you remember, I showed you that sometimes you will have bars. Of course, histogram has bars. You have a gap between 2 bars or 3 bars, something like that, especially at the tails of the distribution. If you have something like that, that means you have here something called the outlier, which is some observation are too large if you compare them to the other observations, or too small if you compare them with the other observation. So these observations, we call them outliers. And unfortunately, these outliers affect most of the statistics we are dealing with, like the mean, for example. So as you can see in this histogram, okay, you have just one small bars at the right tail, okay, and there is about 3 or 4 bars, nothing there. We have this entire gaps, okay? So we consider the first bar on the right as outliers. For example, Suppose you have here the CO2 pollution levels in 9 largest nations measured in metric tons per person. So we have in China 5.9, India 1.4, United States 16.9, Indonesia and Brazil, all these 9 nations. Okay. As you can see here, we have 9 numbers, and if you put them in order, so you can find 0.3 for Nigeria first, 0.4 for Bangladesh, and then 0.8, 1.4, and until 16.9. So put the data in order, and also you can put them on, as you can see here, what is this chart, if you remember? The dot plot, right? This is the dot plot, okay? You can put them on the dot plot as you can see here. If you calculate the median, if you remember, we have 9 numbers. So that means we have just one number in the middle, and this number is 1.8. So on the chart here, on this chart, where we can find the median, okay? You can find the median here. As you can see, you can find the median here. This is the median, right? What about the mean? If you calculate the mean, you will find it's 4.6. Where is the mean on this line or this chart? It's here. Okay, so if you look at these points, most of the data we can find where on the left. You have about 6 points on the left, as you can see here, these points. So we have 6 numbers here. These are the majority of data. We can find them here, right? The median is there between them. These are the majority of our data. We can find them there. The median also is there. The median also is there. But look at the mean. The mean is outside this 6 points, as you can see here. It's outside. So what that means? That means the mean here is not the correct center of our data. Why? Because it's affected by some outliers, as you can see here. Of course, we can consider 16.9 an outliers, and we will have a way to figure out that. We will learn that after a while, okay? But consider that these 3 numbers are outliers. So what happened to the mean? It's shifted from the middle of the majority of the data toward the outliers. So the outliers affect on the mean. Look at the median. No, the median is so strong. It's robust because it's still there. It's still there between the majority of our data, as you can see. So we can conclude from that the mean is not a good measure for center if we have outliers. But the median is a good measure of center if we have outliers. Why? Because it's robust, as you can see. Okay, so we can conclude this from this chart, as you can see here. Of course, we have a way, as I said to you, to figure out where our outliers in our data. Okay. So as you can see here, based on the comparison between the mean and the median, without the graph, you can determine the shape of the distribution. Just you need to compare between the mean and the median. From them, you can figure out what is the shape of the distribution. Is it skewed to the left, skewed to the right, or symmetrical? How? Very simple. If the value of the mean is so close to the value of the median, that means the shape of the distribution is symmetric. If the mean is smaller than the median, so it's skewed to the left, the shape of the distribution. If the mean larger than the median, so the distribution is skewed to the right. Here you have the symmetrical distribution, as you can see here, the green one. Approximately the mean is equal to the median. As I said to you, said what? I said approximately the mean and the median are equal. So what that means? It doesn't have the same value. Okay, so just to close to each other, we can conclude that. But if we have a big difference between the value of the mean and the value of the median, and the mean less than the median, so it's skewed to the left. The distribution is skewed to the left. And same thing, if the median less than the mean, as you can see here in the pink chart here, you have the distribution is skewed to the right, as you can see. Look at the median, the mean in the skewed distribution. Look at the mean. What you can see here, you can see always the mean close to the outliers. Always the mean close to the outliers, right? But the median is robust. Okay, always you can find it approximately in the middle of the distribution, as you can see. Okay, so because of that, I said to you, if you have outliers in your data, you have to select the median as a center of the data, not the mean. But if you don't have outliers, so the mean will be the best measure of center of the data in this case. So what we talked about the robust, or it doesn't shift toward the outliers, means resistant measures. So this topic is about resistant measure. Which measure of central tendency is resistant or robust? Okay, so as you can see here, this is the definition of resistant measure. So if you have a numerical summary measure is resistant if extreme observation have little influence on its value, like the median. The median is robust, is tough, because the influence of the outliers is too small. But the mean is not like that. It's influence a lot in this case. So in this case, we have, it's not resistant measures in this case. So this is the conclusion. The median is resistant to outliers, and the mean is not resistant to outliers. So because of that, I said to you, if you have outliers, the best measure of center will be the median. If you don't have outliers, the best measure of the center is the mean in this case. The third measure of the center is the mode. So far we have three measures of center, the center. We have the mean or the average, we have the median, and then we have the mode. Okay, what is the mode? The mode is the most frequent value in our data, or the highest bar in the histogram. If you remember the histogram, if you have just one peak, the highest bar is the mode. And the mode is most often used with the categorical data. And to forget that, we have two types of data. We have quantitative and categorical. So, categorical means you don't have numbers. You don't have numbers, but you can find what frequencies for each category, right? So the mode in this case will be the highest frequency of the group. So this group is the mode in this case. Okay, but the mean and the median, we can find them from the numbers, right? So you have to have here quantitative data, not categorical data. Okay. Of course, you can find the mode also for quantitative data if you have the histogram. So the highest bar in the histogram will represent the mode in this case. Okay. So how we can find the mode in Excel? Actually, you have multiple functions there, but if you need just one mode, so you can use mode dot SNGL, it's a shortcut for single. So which means you will have just one number for the mode. Okay? And then select the data. So we have multiple functions there. So that means the mode sometimes is not a single value. Yes, the mode sometimes is not a single value. You may have more than one value for the mode. If you remember last time for the shape of the distribution, we said what? We said that sometimes we have one peak, but what if you have two peaks? So in this case, we call it biomodel. Biomodel, right? Here you have two peaks. What that means? That means you have here two modes, not one, two of them. Okay, and sometimes you have more than two peaks. You have three or four. So in this case, also you have three or four modes in this case. Okay, and sometimes you don't have a mode at all. When if the distribution is flat, so there is no peak, there is no mode in this case. Here, in this example, we need to find the mode of this data. We have here 10 numbers, okay? Of course, you can put them in order. For the mode, you don't need to order them, but sometimes it's nice to order them so you can see the repetition of the data. You can find here, you have 3 sevens and 3 nines, right? 3 sevens and 3 nines. So in this case, you have here two modes, not one, as you can see, okay? This is a nice question. Look at this question. For which of the following sets of data would the mean be an appropriate way to summarize the data? Okay, here we have 1, 2, 3. We have 3 cases. The first one is ages of student in Mass 224. The second one, 5 homes costing 300K, 320K, 270K, 210K, and 8 million. Okay? The third one, the data represented in this histogram. So which cases we have here? The mean will be best measure of the center. B is not a good, the mean it will be not a good center in this case because you have one home with 8 million, cost 8 million. So here we can consider 8 million comparing it to the other 4 costs as outliers. So we cannot use here what? The mean. You can use the median instead. Okay? The third one, the data represented in the histogram. Look at the histogram here. Yes, it's symmetrical except one bar to the right. This bar represents what? The outliers. So here we have outliers again. So we cannot use what? We cannot use the mean, but we can use the median instead. So the only case we can use the mean as the center of the data is A. Ages of a student in Mass 224 is the correct answer for this question. Look at this one. This one is very, very beautiful question, actually. Match each data set with the measure of central tendency. Of course, again, what are the measure of central tendency? Mean, median, and the mode. Don't forget them, okay? That would best represent it. So you have A is the mean, B is the mode, C is the median. Look at these 3 distributions and let me know which measure of central tendency is best for each one of them. First of all, you have to know what is the type of your data. The type of your data. So for EQ3, the carbon emissions in tons per capita, okay, we can say this type of data is quantitative or categorical? Quantitative, correct. So we have these numbers, the emissions, we have 19.6, 2.1, 5.8. So in this case, I can choose between just two measures, the mean or the median. Which one of them who will let me know if I have outliers or not? Do I have outliers here? Yes. For Qatar, this is the big number of emission, so we consider it an outlier. So the median is the correct answer for EQ3 in this case. Okay? For EQ2, the first distribution, what is the type of the flavors data? Flavors. So the flavors here, we have cherry, bubblegum, lemon, lime, orange, raspberry. So what are these? Are these numbers or groups or what? They are groups. Yes, they are groups. Categories here. So what is the type of the flavor data here? It's a categorical. So I cannot choose the mean or the median in this case, but I can choose the mode to know what is the center of this data. And of course, because cherry has the highest number of orders, it's 60, so the mode here is equal to 60. For EQ1S, this distribution is talking about what? US unemployment rate. So it is quantitative or categorical? Quantitative, right? So again, we can choose between just the two measures, the mean or the median. Okay, so look at these numbers. We have 8.9, 9.1, 9, 8.5, 7.8. So all these numbers are close to each other. There is no outliers. I can use the mean as a center of this data or to find the center of this data in this case. Okay, so the correct answers for EQ2 is the mode, for EQ3 is the median, for EQ1S is the mean. Okay, so don't forget, if you have a question like that, first thing you have to ask yourself this question: what is the type of the data I have here, or the variable I have here? Is it qualitative or quantitative? If it's or categorical, I mean. If it's quantitative, so I have just two measures, the mean or the median. Which one should I choose from them if I have outliers or not? If it's a categorical data, so I have just the mode I can use to find the center of the data, as you can see. Okay, so this is the end of chapter 2, part 2. Chapter 2, part 3. In this chapter, we continue our measures, because the center of the data is not the only measure I need to describe the distribution. I need something else. What about the variation of the distribution, right? How this distribution is spread out away from the center. So I have to describe this as well. So this is the rule of measuring the variability of quantitative data, or sometimes we call it the measures of variation. The measures of variation. Okay, so here we will look at these two distributions before we can talk about the measures here. Look at these two distributions. Both have the same center, right? The center, as you can see here, in the first one is 5 to the left, and the distribution to the right also is 5. So we have the same center, but look at the distribution here. To the right, we have just one bar, which is more the data around 5, or approximately all the data around 5, as you can see here. But look at the distribution to the left. You have the range from 1 to 9. So which one is more variable? The left distribution or the right distribution? Which one is more variable? Yes, the one on the left is more variable, as you can see here. But the on the right is more consistent. Most of the data are close to each other, as you can see here. So, as I said to you, you don't just need the center of the data, also you need to know the variation of the data. So you can describe the distribution completely right, okay? Look at this example. You will like this example actually. Here you have two distributions, right? Actually, this distribution represent the grades, or we have here two classes, class A and class B, and the distribution here is about the grades for each class, okay? Which class you would like to be in? So first of all, look at the center. Do have the same center? These two classes? Yes. Look at the two small triangle, the red triangle down there. Do you see it? So it's at 80. And the same thing for the class B at 80. So you have the same center. The only difference between them is the variation here, the variability of these two distributions. Okay, you are correct. You select the class A. You would like to be in. Why? Because the minimum is 75 and the maximum is 90. Okay, so at least if you don't have a good grade in this class, will be 75, right? This is the minimum score there. But look at the second class, class B. We have the range from 40 to 100. Oh, we have here a lot of variation, right? So if I did bad in this class, my grade would be in the 40 or 50, right? So you don't like to be in this class. Of course, if you did well, you can get 100, but it's not it's well in the class. So for class A, at least you guarantee the 75, the minimum number. But for the second one, you have 40 or 45. So this is not a good grade in this case. So as you can see here, the variability is very important to measure for the distribution we have. So you can determine which measure, which distribution is better than the others distribution. Okay. So measure of the variability here, we will talk about two measures, the range and the. We will start with the range because it's too simple to find the range of your data. Too simple. All you need just two numbers, the minimum number and the maximum number. Okay? So find the difference between them so you have the range of your data. So the range is equal to the maximum number minus the minimum number. Of course, the range must be positive. Okay? So because of that, we say here, we think here maximum minus minimum, not the opposite. Okay? Okay. But unfortunately, it depends on just two numbers of this data. So what that means, if one of them or both are extreme values, outliers I mean, so the range will be so wide, okay? So it's not a good measure for the variability if I have outliers in this case, okay? So in this case, I need another measures for the variability which can use all data we have, not just the two numbers, okay? So in this case, before we can go to the next one, this is a quick example for how to find the range. As I said, this is very easy. All you need, find the minimum number and the largest number. So in this data set, you have here the minimum number is 1, the maximum number is 7. So the range is 7 minus 1 is equal to 6. as you can see here. So as you can see, it's so easy to find a compute and also the understand the range, as you can see here. And then we have some disadvantages. The first one, it's affected by the outliers, because if you have outlier, that means that the variability will be so high. And also it's insensitive to change in data spread. So as I said to you, I need another way to find the variability of the data I have better than the range, because the range is just based on two numbers. I need to use all information I have. I need to use all data I have to measure the variability. So in this case, before we can find the standard deviation, you have to know what is the deviation. We said that standard deviation, right? So what is the deviation? As you can see from this definition, the deviation of observation x from the mean x bar is x minus x bar. So this is the deviation. It's how far the value of x from the mean. Okay? So we need to measure this distance from the mean to x. Okay? So it's the difference between x minus x bar. But we will do this not for just one number or one data. We will do this for all data we have. So in this case, we need to find the sum of the deviations. Okay? But unfortunately, if you do this, you will find that the sum of the deviations is equal to 0. You can't write this for any data set. Write any numbers. Find the mean. Find the deviations for each number, x minus x bar, and find the sum of these deviations always equal to 0. Because some deviations are negative, some deviations are positive. They cancel each others, so it's equal to 0. Try it at home, or this property is correct, okay? So this doesn't solve the problem, because I need to have a number, right? 0 is not a number. 0 means nothing, okay? So I need to have, I'll solve this problem. To solve this problem, we have to square the deviations. Square the deviation. So instead of x minus x bar, we will say x minus x bar all squared. So what happened here? We deleted all negative deviations and we have just positive deviations, right? But don't forget they are squared. So we doubled them. We doubled them, okay? So instead of deviation, we have deviation squared. Okay, we doubled them. So what that means? That means if you measure your measurements in centimeters, when we find the deviations will be also in centimeters. But when we square them, becomes what? Centimeters squared. So it's double. Okay. So now, when you try to find the sum for the squared deviations, you will have a number in this case, okay? So the standard deviation, as you can see here, this is our equation, is what? It is square root of the sum of the squared deviations divided by n minus 1. Divided by n minus 1. Okay? I will add this part. This is sample standard deviation. Okay? This is, S here is the sample standard deviation. Do you remember we talked about the sample mean and the population mean? There is no difference between them, actually. The only difference is we calculate it from the sample or calculate it from the population. This equation to find the standard deviation from the sample. So we call it the sample standard deviation. And look, you divide by what? N minus 1. N minus 1. But the population standard deviation is equal to this. We will call it sigma. Okay, sigma. This symbol is sigma. If you remember, mu is the population mean. Sigma is population standard deviation. Is equal to what? Is equal to square root of the sum of x minus mu squared divided by n. Okay? So, as you can see here, we have a difference between them, right? For the sample standard deviation, you use x bar, the sample mean. This is the first difference. The second one, you divide by n minus 1, not n. Okay? And if you remember, n is what? The number of data in my sample. Okay? So this is the two differences here. For the population standard deviation, you find what? The population mean, mu, right? Because you calculate the measures from the population. So you can find the population mean. So you use mu, not x bar. The second difference is n, the uppercase n. We divide by n, not n minus 1. And the n here is what? The total number of data in my population, as you can see. So this is the difference between them, okay? And very important to note here, this one, the larger the standard deviation S, the greater variability of the data. Very important, this one. So that means if you have two groups of data and they have the same center, the same mean, you can compare between the variability by the standard deviation. Okay? But I said, we have here one condition. What is this condition? Both groups has the same center, the same mean. So you can use the standard deviation to compare between the variability between them, of them. Okay? So here you can find the calculations of the standard deviation. So if you have data, how we can find the standard deviation by hand? Okay? Because sometimes you may need this for solving small questions or something like that for small data. Okay? So suppose you have here 5 numbers. These numbers are here. 21, 25, 30, 15, and 4. Okay? So these are our data. It's a sample. Okay? So first, find the x bar. So x bar is equal to 19. Do you remember how we can find it? X bar is equal to 21 plus 25 plus 30 plus 15 plus 4 divided by 5. So you will have 19. This is x bar. So find the x bar first. And then start to find what? The deviations. As you can see here, look at the deviations here. These are the deviations. X minus x bar. These are the deviations. Okay? So the first deviation is 21 minus 19. The second deviation, 6 minus 19. I said 6. Oh, sorry. 25. It's 25. 25 minus 19. The third deviation is 30 minus 19. And then 15 minus 19. Last one, 4 minus 19. Okay, so these are the deviations of our data. Okay, x minus x bar. Look at the sum of the deviations is equal to 0. Why? As you can see here, you have 11 plus 2, 13. 13 plus 6 is what? 13 plus 6, 19. Okay, it's a positive. Look at, you have also negative deviations. -4 and the -15. So it's a -19. So it's a 0. That's total. Here is 0. Always you will find that. Okay? Have any data. Find the deviations for them. You will find that the sum is equal to 0. Okay? So because of that, we squared the deviations. So we have this column. These are the deviations squared. Okay? So we started to 2 square is 4, 6 square 36, 11, 121, 4 is 16, 15 square 225. Now you have a number for the total. So the sum of x minus x bar square is equal to 402. Okay, or 402. Now you can find or divide the sum of the deviations square by n minus 1. So n here is 5. We have 5 numbers. So you have here 402 divided by 5 minus 1 or 4. So you have 100.5. Okay? Actually, we call this amount or quantity S square. And the S square means the variance. Oops. Or here the variance. So S square is the variance, okay? As you can see. So the standard deviation is the square root of this number, 100.5. So you have 10.025. So this is the standard deviation of our data, as you can see. Okay? So this is the way of calculating the standard deviation by hand. Okay? Don't forget that. It's, actually, by the table, as you can see here, it's better than you do that without a table. It's more organized. You will not make any calculation mistakes or something like that. So it's more organized than anything else. Look at this example. We have here women's and men's ideal number of children. So for men, we have 0, 0, 0, 2, 4, 4, 4. For women, we have 0, 2, 2, 2, 2, 2, and 4. Okay? Both men and women have the mean 2. So the mean here, x bar, is equal to 2. And here also, x bar is equal to 2. Okay? And they have the same range, right? Huh? So the range here from 0 to 4. So this is the range is 4 minus 0, so it's 4. Same thing here, the range is 4 minus 0 is equal to 4. They have the same range, okay? But the standard deviation, S, for the men group, S here is equal to 2. And the S here for the women is 1.2. So which one is more variable? Which group is more variable? As I said, previous note, the larger the standard deviation, huh, the larger what? The variability or the variation. Okay? So because we have here the standard deviation for men group is 2, it's higher than 1.2 for the women. So which one is more variable? Huh, the men group is more variable than the women group. Okay? So we have, of course, some properties for this measure of variation. As you can see here, the first one, and we already know it, the larger the standard deviation, the greater the variability of the data. It's a very important one. Of course, S measured the spread of the data. Okay. If S is equal to 0, what that means? That means you don't have variability. You don't have variation. And this will happen if all data is equal to specific number. All data is 5s. All data is 3. All data is 1s. All data is 100. So in this case, you don't have any variability, right? You have just one number for all data. So in this case, the standard deviation is equal to 0. Okay? Otherwise, always S, the standard deviation is positive number. It's not negative. Always S greater than 0 means always positive number. Okay? The standard deviation S has the same unit of measurements as the original observation. Yes, because as I said to you, if our original measurement is centimeters, so the deviations also will be centimeters. We squared it, so we have centimeters squared, and then we took the square root. So we return again to what? To the centimeters, right? So the standard deviation has the same unit of the original measurements we have. But the variance, let me return it to this one. Look at here for this example. This is the variance, S squared. So 100.5 here is the deviations square, or the average of the deviations is squared. So if this data with centimeters, so this number is centimeters square. And because we take the square root again, so the standard deviation S will be with in centimeters again. Okay, so we have the same original measurements of our data, as you can see. Okay. S, the standard deviation is not resistant. Oh, what that means? That means if we have outliers, what will happen? The variability here will be so high because it's what? It's not resistant. Why it's not resistant? Can someone tell me why? Huh. Actually, it's obvious. Obvious from what?
Because if you have outliers, it will affect your variance, and then it will affect your population of the.
Okay, let me help you to answer this question. Why? I will return to here. Look at the equation here. The standard deviation, when we calculate it, it's based on what?
The difference between the observation
Uh-huh.
and the mean.
You said what? The mean. The mean. This guy, the mean. X bar is resistant or not resistant to outliers? It's not resistant. It's not robust. So because of that, S also is not resistant. For the same reason, because you use X bar and the X bar affected by the outliers. So the same thing, S also affected by the outliers. Okay? So this is the reason why the standard deviation also is not resistant. Okay? Someone can ask me, okay, what is the measure of the variation which is resistant to the outliers? We will come to it after a while. Okay? But before we can go to or continue, Excel functions to find the variance or the standard deviation. Here you have 4 functions, as you can see here. You have for the sample variance, S square, you can find it by var.s. VAR means variance, S for sample, okay? And the sigma square, this is the population variance. It's also var, VAR, dot P for population, okay? And the same thing for the standard deviation, STDEV, it's a shortcut for standard deviation. It's a function for the standard deviation. Dot S for the sample, dot P for the population. And I showed you what is the difference between them. One of them you divide by n minus 1, and for the population you divide by n. This is the only difference between them. Okay? Okay. So now we have a group of statistics we can calculate. We have central tendency measures and variability measures, right? So we have a computer, we have Excel. So when we have a data, we will calculate each one of them by one by this way. No, actually, you have a very nice way to find all these measurements in just one click, or 2 clicks, 3 maximum. Okay, I'll show you. Actually, you have here an example for Excel. I will show you, of course, how to do that in Excel as well. But let me talk about the example here first. Here you have 2 data about big banks and the best banks. You have the data here. This data about rating the customers about the service there in these 2 banks. Okay, and then we need to find the mean, the median, the mode, the standard deviation, the variance, the maximum, the minimum, all these measurements, okay, for these 2 groups together, okay? I mean separately, but in just one method, okay? So as you can see here, you will use data analysis icon. If you remember, we used it last time for the histogram. So today also you can use it again, but this time you will use something else. We call it descriptive statistics. So after you go to the data analysis and you will have the window, this one. So you will choose descriptive statistics. And from descriptive statistics, you will select the data. So in input data or input range. And then if you put the data in columns, you will say it's in columns. If it's in rows, so you will say it's in rows. If you select the labels in the first cells, so you have to click on labels in first row, and then you will determine where you would like to have your result, final result, okay? And then, of course, you will choose here any empty cell in your sheet, and then you have to choose summary statistics. Without it, you will not have anything. You have to choose summary statistics. And then press OK, and you will have a summary statistics like this. You will have the mean, the standard, or standard error, we will talk about it when we come to it, the median, the mode, the standard deviation, the sample variance. Also, there is more than what we have in this class. We have the quartiles, the skewness, the range. We have the range, the minimum, the maximum, the sum of the data, and the number of the data, which means the count. As you can see here, you have these statistics for these 2 banks separately, as you can see here. Okay. So how we can find them? Okay, let me share with you the Excel sheet I have. As I said to you, this Excel sheet also on the blackboard, so and it's solved as well, so you can go to there and see what happened there. Okay, let me just find it first here on my lab. So we have it here. Okay. Okay. So I will share it with you. Yes. Okay. So as you can see here, this is our chapter 2 Excel demo. As I said, it's on the blackboard. Down there you have different sheets. As you can see, when you click on them, you have the data, as you can see here. Okay. And okay, I will show you how to find. Let me just enlarge it a little bit. Yes. So in this sheet, you have the EBA mileage. You have just one number, one variable here, or one data set, as you can see in the first column. And then if you would like to find the mean, the median, the standard deviation, the variance, separately, each one of them one by the functions. As I said to you, you can use the functions we have. For example, if you would like to find the mean of this data, so you will start with equal sign and then average. Just to start to write average, you will find it in this small menu, okay? And then select the data you have here in the first column and then enter. So the average, as you can see, is 360.994. Okay, so again, this is the equation, average, and select the data in the first column. So you have the average. Okay, same thing for the median. So it's equal median. You have the function here, median. Okay, and then select the first column. So you have the median. Okay, as I said to you, don't need to order them. It's already ordered in the background. Okay, to find the mode, you have mode dot. As you can see, you have mode mult, M-U-L-T. It's a multiple, and single, SNGL. You can use single. So if you don't have mode here, you will not give you any result actually. Okay, we'll choose single, and then the data, enter. So it's 37 as well. Okay, very good. Find the minimum. So it's the minimum function, MIN. Okay, you can find it here. And then select the data, enter, so you have the minimum. Same thing for the maximum, it's equal MAX. Select the data, so you have the maximum. Also, you can find the range, but you don't have here a function for the range. You can find them from the minimum and the maximum. So you will type a function. So it's equal to the maximum number here, 44.9 minus 30. So you have the range of the data, okay? The sample variance, so so it's a variance, VAR, so VAR, as I said to you, have VAR B dot B, this is the population, and the dot S for the sample. So because this is the sample, so you will choose var dot S and then select the data, so you have the sample variance. The sample standard deviation is equal to STDEV, and you have B and S. This is the sample, so you will choose .S, select the data, and then enter. Yes.
Sample variance is just what's inside the square root, right?
Yes.
And then the standard deviation is what's inside.
With what is, yes, the square root of the variance. Okay. So the population variance, but we usually don't use the variance because, as I said to you, it's doubled the original units we have. Okay, so we use always the standard deviation, not the variance. Okay, and the population variance, same thing. So it's VAR, but this time because it's a population, so you will choose dot P and then select the data. So you have the population variance. Same thing, the population standard deviation. So it's STDEV dot B, select the data, and then enter. So you have the population standard deviation. So as you can see, you have a difference between the sample variance and the population variance. So it's not too large, but because we divide by n and the other one divided by n minus 1. So this is the only difference between them. Okay. Okay, so this, if you would like to find the statistics we learned here, one by one, by functions. But if you would like to find all statistics, so we have a different way. So you will go to data, okay, data analysis. From this list, select the descriptive statistics, this one, descriptive statistics, and then okay. First, select your data, the input range. So here, of course, if you remember, when you select the data, you need to select them by dragging the mouse. Don't click on the first column. It's not like the functions. The functions, you can click on the column. But here, you have to select the data themselves. So in this case, I will start with the title there and go all the way down like this, okay? So this is the way of selecting the data when you deal with data analysis, okay? And then because our data in a column, so it's already, we have grouped by columns. And then we select the first cell with a title. So you have to select the label in first row. And then we need to find the output range somewhere here, any empty cell here. And then don't forget, you need what? The summary statistics. Summary statistics, okay? And then okay. Look, you have what? The mean, the standard deviation, the median, the mode, the sample variance, the range, the minimum, the sum, as you can see, all in just 2-3 clicks, as you can see. Okay? Of course, if you have more than one variable, okay, as we have in our example in the slides, you will have another column for the mean, the median for the second group. If you have more than 2 variables, you will have also more than columns for each group for the measurements or the statistics we need to find, as you can see in this our slides example. In this part, we will talk about very important rule in statistics. We call it the empirical rule. Actually, the empirical rule can be applied if the distribution is symmetrical. But if the distribution is skewed, actually, we have completely different rule. Okay, it's not in this class actually. So we will just learn about this rule for the symmetrical, or sometimes we call the bell-shaped distributions. Okay, this rule is as follows. You have 68% of the observation fall within one standard deviation of the mean. Okay, and we write that like this: x bar minus mu, and x bar, I said mu, sorry, x bar minus s and x bar plus s. So this is one standard deviation away from the mean, okay, to the left or to the right, as you can see here. And sometimes we call it like this: x bar plus or minus s. So that means you have here one standard deviation away from the mean, okay? Between these two numbers, or it's an interval actually between or within this interval, you have 68% of the observation. Same thing, if you increase the number of standard deviation from one standard deviation to two standard deviations, you will have 95% of the data within this interval or this range. Last one, if you increase the standard deviation from 2 to 3 standard deviations, in this case, you will have approximately 100% of the data within this range. So we write that x bar plus or minus 3 as you can see. Okay. So you can see this rule on this histogram like this. So x bar in the middle, as you can see here. Okay. The distribution is symmetrical, as you can see here. It's not skewed, symmetrical. And one standard deviation to the left, one standard deviation to the right, as you can see here. This is our first interval, the first range. And between these two numbers, as you can see here, you will find approximately 68% of the data or the observation, as you can see. Okay? If you increase it to 2 standard deviation, so you have, as you can see, from here to here, you have approximately, look what I'm doing. This is also including what? The first interval, right? You have 95% of the data. And if you extend that to 3 standard deviation away from the mean, so you will have, as you can see, the entire data or 100%, as you can see here. This, of course, including the previous 2 intervals, as you can see. Okay. So again, we call it the empirical rule. Okay. An example. So remember, I said to you, you need to describe your distribution by 2 things: a center and a measure for the variability. 2 things. Here you will know, or by the empirical rule now, you can describe the distribution by just 2 numbers: x bar and the s, the mean and the standard deviation. And as you see here in the empirical rule, you calculate 3 intervals, right? 3 intervals. The first one is here. First one, the second one, and the third one. 3 intervals. You describe the distribution by these 3 intervals based on the percentage we talked about, the 68%, 98%, or 100%. If that happened to your data, that means the distribution is symmetrical. If not, so the distribution is not symmetrical. It's what? Yes. Any question? Okay, guys? So we will see that in this example. So suppose here you have student train rates to move through a maze. The following table recorded the time of 30 rats running through a maze. So we have the data, as you can see here, in minutes, and we need to compute for this data x bar and the s, the mean and the standard deviation. Okay, of course you already know how to find this now by Excel or by manually. So we can find them here. As you can see, x bar for this data is 3.74 and the s 2.2. Now start to find the first interval for our interval rule. The first interval we calculate is for 1 standard deviation away from the mean, x bar minus s and x bar plus s. X bar 3.74, s 2.2. So our first interval as you can see here, this is of course after we apply them or substitute them in the interval, and then so the first interval starting from the minimum number is 1.54 and 5.94. This is the first interval. Okay, now start to count how many numbers in our data fall in this interval. Okay, so if you return to our data there, here, and start to count the numbers that belongs to this interval, you will find them 23 numbers. Okay, so as you can see here, there are 23 measurements or number within this range. Okay, okay, now we need to find what? The percentage, right? So if you divide 23 by the total number 30, because we have 30 observation, and multiply it by 100, so you will have 77%. So this is the first percentage for the first interval. Redo that again, but for 2 standard deviations. Okay, so for 2 standard deviations, as you can see here, this is the mean. This is 4.4 is 2 times 2.2. This is 2 standard deviation. And here, the same thing. This is for the upper limit. So the range is from negative 0.66 to 8.14. Again, count how many numbers in our data within this range. So you will find it 28 number. Divide it by the total, 30, and multiply by 100. So you will have 93%. Okay? Same thing for the third one. Of course, in the third one, you will find all the data within this range, so it's approximately or 100% of the data. Now, compare between these observations, as I said observation, sorry, these percentages, the 77, the 93, and the 100 with the empirical rule. Okay, of course, the empirical, so to have here 100% actually. Okay, so the first interval, if the data follow the empirical rule, we should have 68% of the data, but we have what? 77%. So it's larger than the 68% on the empirical rule. The second one, we have here for the empirical rule 98%, but actually we have what? 93. It's less than a little bit. So we have a difference, right? But of course, the last one, we have the entire data, so this will not make us make a good decision about the data. But compare between these percentage now. So you have here 77% here, 93%, and 100%. So according to that, are these percentage close to the empirical rule percentage or not? Close or not? They are not close. They are not close enough. Okay, so we can conclude without graphing the distribution of this data that this distribution is skewed. It's not symmetrical in this case because it doesn't, the percentage of this data doesn't follow the empirical rule percentage. Okay, and if you would like to see the distribution, this is the distribution of the data. Is it symmetrical? No, it's what? It's skewed. And this, we confirmed it with the percentage of the empirical rule, with the percentage we calculate for the same interval from the data, as you can see. Okay, so from this example, we can, or you know now how to describe the data you have without graphs, but just with numbers. In this example, by X bar and S, you can describe the data, if it's symmetrical or skewed in this example, okay? Another way you can describe the data, what? If you remember, comparing between the mean and the median. If they are close to each other, so it's symmetrical, okay? If the mean greater than the median, so it's skewed to the right. If the mean less than the median, so the distribution of the data is skewed to the left in this case, okay? So you have now two ways to describe your data, the empirical rule or by comparing the mean and the median together. Yeah.
How close, like, do the percentages have to be to the low percentages to see them symmetrical?
Okay, let me return again to here, okay?
Like, say, instead of the 77%, it actually was 70%. Is it still not symmetrical? Since because like 93% is pretty close to
When I said look at this percentage and the empirical rule percentage, are those close to each other? So the idea is to be close, not exact percentage, close. So for example, suppose for this example, you found that the first interval is 70. The second one is 94. And the last one is 100. So it's okay. It's close to it. So it's empirical. But if it's far away a little bit, especially for the first and the second intervals, so it's not symmetrical. It doesn't follow the empirical rules. So 3.74 is somewhere here, 3.74. So we can say it's somewhere here. So this is x bar. And the standard deviation, 2.2. 2.2. Okay. So we have 1.54, 5.9, 1.54. 1.54, 1.54, 1.54. So 1.54, 5, say this is 1. So it may be here. Okay. And the second one is 5.94, 5.94, 5.9. So it's approximately here. Okay, so this is the first interval. This is the first interval with one standard deviation away from the mean. Okay, from here to here. Okay, okay, to here, for example. Okay, so all these bars represent 70% of the data. So here we have 77% of the data. Okay? So do you see what I mean here? Huh? Okay. And if you do that again for the second interval, of course, we have negative 0.66. Negative 0.66, of course, will be before 0. Okay? Or somewhere here. And the upper limit is 814. So 814, say it's here. Okay, so from here all the way down to the last one, you have here what? 94% of the data, right? It was 94, right? Or something else? Yeah, 93. 93 of the data. So we have 93 of the data. Okay, and of course 100 for all bars in this case. Okay, and as you can see here also, the distribution is skewed. Why? Because you have here this bar. This bar is what? Outliers, right? So of course it makes the distribution skewed to the right, as you can see here. Okay, maybe 8 also. This bar is an outlier. So this, of course, makes the distribution more skewed to the right, as you can see. Okay, but if you have or if the data here follow the empirical rule, it should be close to this distribution or this histogram, as you can see. Okay. Okay, so the measure of the positions. Okay, sometimes it's useful to know what is the position of a specific data or a specific number we have, okay, in our data. We will start with something called the percentile. Percentile, okay? So first, we have here a definition for the measure of the position. As you can see here, descriptive measures of the relationship of a measurement to the rest of the data are called measures of position. So we compare between the measures, okay, or a specific measure with the other measures, okay, to know its position on the distribution of the data, okay. Usually, we compare this if it's above the mean or lower than the mean. And if it's above the mean or lower than the mean, by how many standard deviation. Usually we do this in statistics. We will see that after all. But as I said to you, we'll start with the percentile or the percentile score. This, of course, gives us a measure of the position of the data. To understand this part, look at the example here, and then we will return to the definition. We have a class of 45 students, just had an exam. A student GD was told that his score was 1200, and he scored at the 9th percentile. What that means? That means 90% of the test scores are below or at 1200. Okay? And the 10%, the remaining of the test scores are above or at 12 percentile, the 1200. Okay? So we can see this scenario here. This is the distribution of the test scores. Okay? 100 or 1200, it's the score of our student, JD. Okay? So the 12%, 1200, it's at 9th percentile. What that means? That means 90% of the scores, of the test scores below or at 1200. And the remaining 10% is above 1200. Okay? So from this number, from this percentile here, we have a shape of the data. And also we have a position for this number, 1200. Okay? So if you know this information, you can conclude what? The following. We said we have how many students in the class? 45. Right? 45. So if you multiply the 45 students by the 90% or 0.9, you will have what? This number, 40.5. And if you multiply again the number of students, 45 by 10% or 0.1, you will have 4.5. These are what? The number of students. The number of students lies in the 90% area or the curve, and the 10% of the area, 10% on the area of the curve. Okay? So as you can see here, of course, because we have 0.5 and we are talking about student persons, okay, so we don't have 0.5, so you can round it up or down. So what that means? That means you have 40 or 41 students scored below 1200, and 4 or 5 students scored above 1200. Okay, as you can see. So the percentile, according to this example, is what? For any set of n measurements, arranged in ascending or descending order, the p percentile is a number such that p% of the measurements fall below that number, and the remaining is 100 minus p% fall above this number. Okay, so this is the definition of the percentile. So the percentile is just to open the floor to very important statistics we can find. These statistics, something we call quartiles. The difference between percentile and the quartiles, one thing, percentile for tenths, quartiles for 25%. Okay, so this is the only difference. So the quartiles divide the distribution into 4 areas. Each area of them is equal to 25% of the data. Okay, as you can see here in this distribution. Okay, so in the middle you have Q2, the second quartile, or the median. Q1, the first quartile. Q3, the third quartile. Simply, the median divide the distribution into 2 equal halves, 50% of the data before the median, 50% of the data after the median, right? Okay, now, the first half below the median, consider it a separate data set. Find the median again. For this half, you will have the first quartile. And the same thing for the other half above the median. Consider it a separate data set and define the median. So this is what the third quartile. Okay, as you can see here in this chart, here you have the median or the second quartile. So you have 2 halves, 50% and 50%. Okay. So for the first half, starting from here, find the median again for the first half. So you will have Q1, right? And the same thing for the second half. Find the median again, so you have the third quartile. As you can see, Q1, Q2, Q3, divide the distribution into 4 equal areas, 25% of the data for each one of them. Okay? So this is the way of finding the quartiles. It's like the median. You find the quartiles like the median. First, order the data from the smallest number to the largest number, or the opposite, and then find the median. So this is the second quartile. Okay, and then for the first half, lower than the median, you find the median again for this data set. So this is the first quartile, and the same thing for the second half, higher than the median. Find the median for this data set, so you will have the third quartile. Okay, so this is the way of them. So for example, suppose you have here again the sodium values for the 20 breakfast cereal. What are the quartiles for the 20 cereals sodium values? We have the table here, the number in this table ordered from the smallest number to the largest number. The smallest number is 0, last number is 340. Okay, find the median first. So the median, here you have even number of the data because you have 20. So that means you have 2 numbers in the middle. These numbers are These are the two numbers in the middle, 180 and the 180. So the average will be 180. So this is the median. So QT2 is 180. This is the median of this data. Okay. Then, so between 180 and this 180, we have the median. So the median is here, Q2. So from here to here, from 0 to this 180, this is the first half lower than the median. And from 180 to 340, this is the second half higher than the median. Okay, so now you have two separate data sets. For the first data set, find the median. Of course, you have 10 numbers now. It's even number. So you have two numbers in the middle. So you have these two numbers are 130 and 140. Find the average of them. So this is the first quartile, 135. Same thing for the second half. Okay, you have 10 numbers. You have two numbers in the middle, 200 and 210. Between them, you have the median. Find the average of these two numbers. So it's 205. This is the third quartile. Okay.
What if we had, so let's say you have two
Odd numbers?
180s.
Mhm.
Do you count the 180 in both of the data sets when you're finding the median, or no?
Say that again. Say that again.
Oh, okay. So say you only had 180. 180.
In this data, I have two.
Yeah, but say you had only one.
That means instead of 20 observations, we have 19 observations, right? Okay. So that means you have just one number in the middle, 180. This is the Q2 in this case. Okay, I'm coming to you. So that means one number in the middle. Okay, so now we will ignore this number and take all numbers lower than 180. So you will have how many numbers in this case? Huh? 9. For this 9, how many numbers in the middle? 1. So this will be Q1 in this case. Same thing for the second half, higher than the median. You will have 9 numbers. So in this case, you will have one number in the, okay? Same thing. Do you remember when I said the standard deviation is not robust or resistant, right? Why? Because it's based on what? X bar, and the X bar affected by the outliers, right? And the second question, someone asked me, what is the robust measure of variability? This one, IQR, interquartile range. This is the analog measures of variability if we have outliers in our data. Okay, so now we can summarize two things. If the distribution is symmetrical, so the center of the data will be the mean, and the standard deviation will be the measure of the variability. If the distribution is skewed, so the best measure of center is the median, because we have outliers there, and IQR, the interquartile range, will be the measure of the variability instead of the standard deviation. Okay? Okay? So, how we can find the interquartile range? Very simple. After you find the first quartile and the third quartile, find the difference between them. Q3 minus Q1. So you have the interquartile range, and this gives you how the 50% of the data is spreading on the shape of the distribution, as you can see. Okay. So in Excel, how we can find these quartiles? unfortunately, if you return to our Excel, when we calculate the data, the statistics or descriptive statistics by the data analysis, we didn't find in that list anything about quartiles. We just found what? The median. We don't have anything about the quartiles. Okay? So you can use functions in Excel to find these quartiles. As you can see here, the first quartile, Q1, you can find it by quartile.exe, and then select the data. Here you have two things. You select the data and then one for first quartile. Okay? For the third quartile, same thing, same function, quartile.exe, select the data, but you will type here 3 for third quartile. Okay? Of course, you can, as you know now, the second quartile is the median. So here you have two options: to use the median function to find the median or the second quartile, or use the same function we have here, quartile.exe, the data, and then 2. So this gives you the second quartile. Okay? Do you remember when I said you will know today how to find the outliers in your data? This is the way. Detecting potential outliers. How? Any value beyond 1.5 times what in the interquartile range, we consider it outliers. So first, find the interquartile range, multiply this range by 1.5. Any number greater than this, sometimes we call this this range, or okay, this range or this standard, we consider it outliers. Okay, I think here you will have you will find two fences for the outliers, because the outliers sometimes is too large, sometimes it's too small. So you have to detect these outliers from both sides, from the small side and the large side of numbers we have. You will see that, as you can see here, an observation is potential outliers if it falls a distance of more than 1.5 times interquartile range below the first quartile, or a distance of more than 1.5 times interquartile range above the third quartile. Okay, so what that means? That means if you have a line like this, of course, the median here or second quartile, okay? You have here the third quartile. Here you have the first quartile. Here you have the interquartile range. Okay, now this is 1.5, the interquartile range. This is the 1.5, the interquartile range. Of course, this is the distance below Q1. This is the distance above Q3. So any value in your data greater than here or less than here, we consider it an outliers. Okay? So someone can tell me, we need to see this on a graph. We wanted to see them on the graph. So in this case, you have to determine first 5 numbers. These numbers are the minimum value, the first quartile, the median, the third quartile, and the maximum value. These 5 numbers, we call them 5-number summary. Just you can find them, you can construct something called the box plot. the box plot. Look at the box plot here. This is the box plot. Okay, for the box plot, of course, you have a box here. Here you have the median. This line, the vertical line, is the median. This is the first quartile, and this is the third quartile. So the box here is the distance from the first quartile to the third quartile, or the interquartile range. Okay, and then you calculate, as I said to you, 1.5 the interquartile range for both sides. Okay, for both sides, below the Q1 and above the Q2. Okay, so any value less than the distance below 1.5 interquartile range, we consider it an outlier. You will put star like this one. So you will know this value is an outlier. Same thing, the distance above the third quartile by 1.5 interquartile range, any value above this distance, we consider it an outlier. So you put a star like this. Someone will tell me, what about these two lines? Actually, these two lines, we call them whiskers. Whiskers, okay? This is the distance from the first quartile to the lowest or smallest value within the range of 1.5 interquartile range. Again, this is the distance from the first quartile to the smallest number within the distance of 1.5 interquartile range. And the same thing for the other side. This distance from the third quartile, okay, to the largest value within the 1.5 interquartile range. Okay, because above these two limits, you have outliers, and you will put stars to see them on the graph. Okay. So in this example, okay, of course, this is a quick example to find, again, the first quartile, the second quartile, the third quartile, the smallest number, and the largest number. So this to find the 5 number summaries. So simple, you already know how to find them now. And then you construct the box plot, as I said to you. Okay, the box goes from Q1 to Q3, and then the line is drawn inside the box is the median, and then the line goes from the lower and the lower end of the box to the smallest observation that is not potential outliers, which means it's the smallest number within the range, the distance of 1.5, the interquartile range, and from the upper end of the box, this is the largest observation that is not an outlier or within the range of 1.5, the interquartile range. Any value outside the distance of 1.5 interquartile range, we consider it an outlier, and we put a star on the graph to determine it, as I said to you, like this. Okay? Sometimes you can see something like that. You have here two box plot side by side, as you can see here, or in just one graph. This, if you have two groups of data and you want to compare between them. Okay, so as you can see here in this graph, you have two box plots for the based on the gender, male and the female. Okay. These are portray certain feature of the distribution, such as okay. Oh, so this two distribution is based on the height of the students, okay, for male and the female groups. Okay, so as you can see here, from these two groups, you can compare between the height of the male and the females, by this way. First of all, look at the median on these two boxes. The median for the male is here. The median for females is here. So which one is higher? For male. This is the first thing. Usually, the distribution for the male heights is higher than the female heights, as you can see here. Look at this box and look at this box, right? Don't forget, this box represents what? 50% of the data, right? Okay. And then we have a lot of outliers for females height than the males, as you can see here. So which one is more variability is the distribution of height for females, as you can see here. Okay, why? You have here outliers. These are too short females. These are too tall females. Maybe comparing also to the most of, or 50% of the males as well, as you can see here. Okay, so if you have two groups, you can use the box plot to compare between them by this way. Okay, so very, very nice graph for your distribution. Also, before we can finish this part, based on the box plot, you can determine if it's skewed or symmetrical. Actually, like like the histogram, like the dot plot. Okay, so if you have box plot like this, so we can say the distribution is symmetrical. The distribution is symmetrical because, as you can see, the median in the middle, this distance from here, from the first quartile to here, lowest quartile to here, the same distance here. So the distribution is symmetrical. Okay, but if you have something like this, the distribution is skewed to the right. Skewed to the right because the tail here, or the distance here, is longer than this tail. So it's skewed to the right. Okay. Same thing, of course, for skewed to the left will be like this. So the median is here. This is the longer than this one. So this one is skewed to the left. This one skewed to the right, as you can see. So also based on the box plot, you can determine the shape of the distribution, as you can see. Okay. And also you can detect by the box plot the outliers. You can see the outliers. Okay, like the histogram, when you have on the right or on the left two small bar at the end of the histogram, so this is an outlier in this case. Okay, of course you can find the box plot in Excel very, very easy after you put your data. So all you need is to go insert, okay, go to this icon or statistical. If you remember, we used the histogram, this one. We used the Pareto chart, and now the last thing is box plot, as you can see here. Based on the number of columns you have in your data or the variables, you will have the number of boxes in the graph. So if you have just one column, you will have just one box plot. If you have two or three, you will have two or three boxes on the left. So of course, because we have here two columns, you will have two boxes on the same sheet, the same graph, like this. Okay. Of course, the blue one for the big bank, the orange for the best bank, and here you can compare between them Which one is more variable? The blue or the orange? Which one is more variable? The blue is more variable than the orange, right? Which one has outliers? The orange one had outliers, but this one is not. Which one is symmetrical? Which one is not symmetrical? The orange one is, yeah, is not symmetrical. So the orange one is skewed. The blue one is not skewed. Okay, as you can see here, this one is symmetrical. This one is skewed. Why it's skewed? Huh? These outliers make this distance, right? Make this distance. This is the tail. Okay, so is it skewed to the left or skewed to the right? This is the hard question, right? To the left. Why? Because this tail for the lower values, not for the large values, right? So it's to the left. It's not to the right. Very good. Very good. Okay. How we can calculate this score? To calculate this score, of course, we have Z as a symbol for this score, Z, and you need to have the observation you are interested in, the mean of the observation you have, and also the standard deviation. So simply Z is equal to X, the value we are interested in, minus the mean of X, X bar, divided by S, the standard deviation. Okay? So this is the way we calculate this score for any value we have. Okay? And to detect or to know if this value X is outlier or not, we have the following rule. So an observation from a bell-shaped distribution is a potential outlier if its z-score less than -3 if it's negative, or greater than 3 if it's positive. Okay? So suppose we have a value and we calculate this score for this value and we found it's equal to 2.5. 2.5. So we consider it an outlier or not? Of course not. We cannot consider it outlier. Why? Because it's less than 3. But if the z-score for this value is, for example, 3.4, it's greater than 3, so we consider it an outlier. Another example, suppose we have z is equal to -5.1, -5.1. So it's less than -3. So in this case, we consider the value of X of this z-score as an outlier, okay? So this is another way for calculate or for detecting the outliers from the data. Okay, so we have this example. A sample of 2,000 high school seniors. Verbal sets scores is selected, which has the mean X bar 550 and the standard deviation S 75. Suppose your score is 475. What is his sample z-score? So the sample z-score, as I said to you, is X minus X bar divided by S. So X here is equal to 475. We already have X bar. We have S. So we can calculate this score for this value. And it's found it's -1. So -1, okay? So what that means, -1? -1 means Joe's score is less than the average of the class by 1 standard deviation. So 1 here, or -1 here, this value means 1 standard deviation. So what that means? That means we calculate the distance for any value by a unit. And this unit is standard deviation, like centimeters, like feet, like kilometers, okay? So it's in statistics, Standard deviation is a unit, okay, is a unit. So here, when we say -1, what that means? That means the value 475 is less than the mean 550 by 1 standard deviation. Why I said it's less than or below the mean? Because it's negative. Because it's negative. So we call this below the mean. If it's a positive, we say above the mean. Above the mean by how much? You have the value 1 standard deviation or 2 standard deviations in this case. So again, this is something new. You may know it today. Standard deviation is a unit in statistics. Like in a unit we know, centimeters, feet, inches, whatever, okay? Another example, this example is very, very nice one. Suppose that among college applicants who have taken both the SAT and the ACT tests, their SAT scores have mean 1200 and standard deviation 100. Their ACT scores have mean 28 and standard deviation 2. One student scored 1270 on the SAT and 30 on the ACT. We wanted to see if the student did better on the SAT or on the ACT. Okay, actually we cannot compare between them by the standard deviation, as I said to you last time. Why? Because we don't have the same mean. The only way to use the standard deviation to compare between two groups or two values, you have the same mean for these two groups. But if you have two different groups, you cannot do that. In this case, you will use this score. If you have different means for two different groups, in this case, you can use this score to compare between values in these two different groups of sets. So calculate Z for this score, 1270. Okay, so the mean of this score is 1200, and the standard deviation is 100. So this is X bar. This is S. We can say X bar 1, S1, because we have two groups. This is the first group, okay? And Z for the SAT score is 0.7. So again, 0.7 means that 1270 is above the mean of the SAT scores 1200 by 0.7 standard deviation. This is what we mean by 0.7, okay? So again, 1270 is above the mean by 0.7 standard deviation, okay? We will do that again for the ACT score. The ACT score for this person is 30. The mean of the scores is 28. The standard deviation is S. So we can say this is X bar 2. This is S2. Okay. And we find the score for this value 30 is equal to 1. What that means? That means that 30 is above the mean because it's a positive. 1 here is positive. So it's above the mean 28 by 1 standard deviation. So now we can compare between these two values, 1200 and the 28. Which one is higher in this case? Which one is higher standard deviation? Higher z-score? Huh? Yes, ACT, because it's equal to 1. It's greater than 0.7. So in this case, which test that person did better? In ACT, in this case, because it's 1 beyond the mean of the distribution in this case.
There's 6 people waiting.
Oh. Okay, guys. So as I said to you, this is very nice example. Show you how to compare between two different groups or two different values in two different groups with two different means in this case. Okay. So this is the end of chapter number 2, part 3.